Okay, let's dive into this. The word tensor. You've probably heard it thrown around, and it sounds, well, it sounds like something straight out of science fiction, right? Something super complex, maybe a little intimidating. But what if I told you it's one of the most powerful and fundamental ideas in math and physics, and that you already kind of get it? Let's break it down.
So to get started, we're going to use this brilliant, simple analogy. Forget all the complicated math for a second and just think about Legos. Seriously, this is the absolute best way to start building this concept from the ground up, literally.
All right, check this out. If you have just one single Lego block, that's a scalar. It's just one number, like the temperature, 72 degrees. Now, line a few of those blocks up in a row. Boom, you've got a vector, a one-dimensional list of numbers. Next, arrange them in a flat grid, with rows and columns. Well, that's a matrix, which is two-dimensional. So what happens if you start stacking those flat grids on top of each other to make a cube or a block? That's it. That's a tensor. And, colloquially, especially in fields like computer science, a tensor is often just seen as a generalization of all these things. Basically, a multidimensional array.
And that right there brings us to the most important question. If it's just a fancy word for a multidimensional array, why all the fuss? Why don't we just call it an n-dimensional array and call it a day? Well, it turns out that simple, convenient definition is hiding a much, much deeper truth.
You see, the real reason tensors got their special name doesn't come from computer science at all. It comes from physics. The why behind tensors is all about a fundamental quest to describe objective reality, no matter how we, the observers, happen to be looking at it.
This quote from NASA physicist Joseph C. Kalecki it absolutely nails the core idea. Think about it. Physical reality doesn't care about our maps or our rulers. A force, the wind, the curvature of spacetime, these things exist out there, objectively. And so the mathematical tools we use to describe them have to reflect that independence. They have to work no matter our point of view.
But let's make this super concrete with a simple example. Imagine a wind that's blowing directly north. For observer 1, whose map is aligned perfectly north-south, the description is easy. It's moving 10 kilometers per hour north and 0 east. Simple. But now look at observer 2. Their map is rotated. To describe the exact same physical wind, their numbers are totally different. Now it's a mix of northeast and northwest. The key here, the really crucial point, is that the wind itself didn't change one bit. The physical thing is the same. It's our numerical description, the components, that changed because our coordinate system did. A true tensor is a mathematical object built specifically to handle this exact problem.
So for a mathematical object to really represent this coordinate-independent reality, its components can't just change willy-nilly. When you change your point of view, they have to change according to a very specific, predictable set of rules. And this is the absolute heart of what a tensor is.
And here it is, the formal physics definition. A tensor isn't just a box of numbers. It's a box of numbers that comes with a promise, a guarantee, called a transformation law. This law ensures that no matter how you twist or turn your coordinate system, the underlying physical thing it represents stays exactly the same. This transformation law is the bright red line. It's what separates a simple grid of numbers, just the plain old matrix, from a true rank 2 tensor. We actually classify tensors by their rank, which you can basically think of as how complex its transformation rule is. A rank 0 tensor is just a scalar, a single number. It's simple. It doesn't change at all when you change coordinates. A rank 1 tensor is a vector, and it transforms with one specific rule. A rank 2 tensor, which looks like a matrix, needs 2 of those rules to keep its meaning. And an n-rank tensor? Well, you guessed it. It needs n different rules. The higher the rank, the more complex the object.
But hang on, because there's an even more beautiful and honestly more powerful way to think about tensors. It's a way that goes beyond just memorizing rules and gets to the very essence of what they're made of.
This is probably the most elegant definition out there. Instead of defining tensors by what they do, how they transform, we can define them by what they are. They're built from these fundamental atoms. You have vectors, which you can think of as arrows, and their counterparts, covectors, which are more like stacks of surfaces. These are the two basic types of building blocks, and they get combined using a special operation called the tensor product. So the huge takeaway here is that vectors and covectors are the basic Legos. The tensor product is how you snap them together. This means a rank 2 tensor isn't some abstract thing anymore. It's fundamentally a pair of these building blocks. And this inherent structure, this construction, is the deep reason why they follow the specific transformation laws we talked about earlier. The rules aren't just arbitrary, they're a direct consequence of what a tensor is actually made of.
Okay, this is all fascinatingly abstract, I get it, but where does the rubber meet the road? I mean,
where do we actually use this stuff? Well, it turns out tensors are not just some mathematical curiosity. They are absolutely essential tools that have shaped our understanding of the entire universe and are now powering our future.
And the idea has been around for a while. The name itself is coined way back in 1846, but it was the work of mathematicians like Ricci and Levi-Civita around 1890 that really built the machinery. And then, and this just shows you the power of a good idea, in 1915, Albert Einstein realized this was the exact mathematical language he needed to describe gravity, which led directly to his theory of general relativity.
And that is not an exaggeration. The very fabric of reality, spacetime, and how it bends and warps in the presence of mass and energy is described by a mathematical object called the Riemann curvature tensor. It's what tells us that gravity isn't a force pulling us down, but rather it's just the geometry of the universe we live in, a geometry described perfectly by tensors. Now let's jump forward to today. In machine learning, we're kind of back to that multidimensional array idea, but for a really important reason. Look at these handwritten digits. Each one is a grid of pixels, right? Maybe it's 16 by 16. If we just flatten that image into one long single list of numbers, a vector, we'd lose all the spatial information. We'd lose the fact that some pixels are next to each other. By treating it as a ranked 2 tensor, we preserve that crucial 2D structure, which is absolutely vital for an AI to learn how to see and recognize the image.
So at the end of the day, we have these two seemingly different ways of looking at tensors. We have the computer science view, and we have the physics view. How do we square these two ideas?
Well, they're really just two sides of the same coin. The computer science and machine learning view is focused on the what. It's a practical data structure, an array of numbers that libraries like PyTorch and TensorFlow use to organize really complex data. The physics and math view is focused on the why. It's a fundamental geometric object whose meaning goes beyond any single point of view. The data structure is the representation. The geometric object is the reality.
And that leaves us with this one last thought to chew on. We started this whole journey with a simple pile of Lego blocks, and we ended up with the curvature of spacetime. So it really makes you wonder, is a tensor just a convenient way to organize numbers in a computer, or is it a true mathematical shadow of reality itself? And the beautiful answer is that it's both.